So we have a problem, and the problem I found is here. So this relay is labeled L, and it's got these contacts, and it's right in this spot on the mounting plate, so I can go look at it. Let's go look at it.
Can you go to Plat or wherever they got it? And yeah.
Yeah. All paths have been blocked. Okay, so L relay, L relay, L relay. Where are you, L relay? There's the L jack. Looks like the L relay is mysteriously absent. And that is really, really important. The L relay is extremely critical to the operation of this sender. So that puts this project completely on hold until I can find an L relay. What we need to do now is figure out what kind of relay the L relay is. Well, this will tell us it's either a 239HE or 280W, and it depends on what options you have. You can either have option FO or FP. FO is the older, FP is the newer. So either one of those relays can be used to replace this. Let's go ahead and see what a 280W is. So here we are in our card file. And we find the card for 280W. And here it is. We can see 280W has 3 windings, a primary, secondary, and tertiary. Here's the number of turns on each winding, and the number of resistance, the resistance in ohms for each winding. So this tells me that this is a fairly special and particular relay. I can't just substitute this for something else, because these other ones that are similar, they look the same, but this only has primaries and secondaries. This only has a single winding. Primary and secondary single. So the 280W is not something that I can just replace with any old relay. It's really special. Damn. I was looking around for a 280W in a circuit that we're not using that I could steal, because there's a few of them around here, and if I can find one that lives in a circuit that's never going to be used, then I'll just take it. And the only problem was, the only place I found one was in this sender circuit. Now, yes, this sender circuit isn't being used. However, it will be used someday, and I don't want to steal this 280W from an otherwise perfectly good sender that sooner or later I will get working. It seems like robbing from this to put it in the other sender just makes it so this will never work. So that's not a good idea. One of the questions I get most often during tours from guests is, do you have enough parts for all this stuff? Or what happens if you don't have parts? Do you make them? And that's actually a really good question. There's a lot of things that we do have spare parts for. These busy plugs. We got about 1 billion of them. We're going to be fine. These things, we've got tons of them. We're going to be fine. But there are certain things, like relays, this one in particular, that we don't actually have very many spares of, if any. And that's the kind of thing that worries me, because it's the relay is the kind of thing that would be difficult to manufacture, There's nothing you could really use to substitute it. There's nothing that's close. There is no close. There's either this relay or literally any other relay that's not the right one. And it's also very, very important, very critical relay. This is when the issue of needing and finding parts becomes a problem. This is right here. This is it. What am I going to do about it? A few things. We do have an attic. It's not here, but we do have an attic. I'm going to take a trip down there and see if I can find, maybe there's that relay lying around there somewhere. The only problem is I can't film there because it's a secure location. But I'm going to go there right now, and I'll come back and we'll see if my search turned up anything good. Yes! Okay, I found it. This is very good and also very bad. It's very good because I found the relay. Here it is. It's in great shape. It's never been used before. There's the mounting hardware for it. Awesome. Problem is, this is the only one we have. So I'm going to go use it in that circuit over there. And then if I ever need one ever again, I'm out of luck. So good that I found it. Bad that this is the only one we have. Because again, this is a very specific relay, and if it were to break, there isn't anything else that I could replace it with, and it would be a huge hack to get it to work without it. So, okay, I got the relay in. I had a bit of an oh shit moment because I realized that I previously put a resistor in way back, like a couple weeks ago, and that resistor was connected to that L relay, but since there was no L relay there, the resistor wasn't doing anything. But my mistake was that the resistor I put in was not capable of handling that that dissipation of current. So when I put the L relay in, hooked it all up, everything's cool, I run the test, see where we're at, and the damn L relay starts smoking. And I really didn't want that to happen because that's the only one we got. So I quickly ran behind the sender, saw that this resistor was just melting, so I ripped it out of there, saving the L relay, thank goodness. And then when I thought about it, that was this little tiny resistor, and I should have known that it would not be able to handle that kind of current. But anyway, it was fine. I caught it before it did any real damage. And now the L relay is in there, and it's looking really good. The sender itself has advanced to the point where 16, 18, where's 20? It's advanced to the point where we should be getting somewhere really soon, which is cool. I'm totally stoked about that. So I'm just waiting for Andrew and Astrid and Colin to show up because I'm going to need 2 people for the next part of this. Currently where we're standing is now that the relay is in, the sender is pretty much ready to go, except it's not releasing. It's not releasing itself, or it's not releasing the controller circuit. Why is it not doing that? Something to do with the GS lead. Where's the GS lead? Don't know yet. So I figured while I talk, I would sort these drawings out because I made a complete mess of them. That way, when it comes time to move on to the next thing, everything is more or less where it should be. 11, 10, 10, 10, we're missing it, there we go, 10, 9, 9, 9, okay. So I'm pretty excited about that. The sender's doing a lot more cool stuff. All kinds of cool clicks going on. And I bet if we can get this GS relay thing sorted out tonight in the next few hours, I'm sorry, GS lead, not relay, we'll probably get this thing to advance and do some stuff, which is cool, and I'll get that on film for you guys. So anyway, I'm going to continue sorting these drawings and wait for them to get here. And when they do, we will pick up where we left off and keep charging on. Andrew's soldering. He doesn't realize that I'm filming.
Is there any chance we could get a lamp?
Yeah. Be right back. Wow, okay. It's been a few days since I last filmed. I think it's been... must have been about a week since I got the L relay from storage. And we put it in, and the test is still failing. And the tough part, and part of the reason I haven't filmed for a week, is that we've just been kind of running in circles. So where we're at right now with the test frame is, it's reached a point where 3 or 4 distinct things kind of come together and converge on this one point, and then the test proceeds from there. And when you have that many balls in play, it's hard to figure out why it's failing at this point. It just so happens that the 3 or 4 things that are converging are all in themselves complex operations, and everything has to happen in the right sequence at the right time and in the right order, and that sequence and timing happens to be too fast to like stop it and go through the operation of each relay. It just doesn't work like that. So we were running in circles. There's a lead that runs out from the test frame, through the sender link, into the sender, through a few relays, back out to the sender link, through a terminal strip, back out across the office, and then back into the sender test frame on a different terminal strip. And that was part of the thing we were chasing. Like, did we connect all these? Did we connect all the segments of this lead correctly? I think so. It looks like we did, but maybe we screwed something up. The terminal strips are sometimes unlabeled, and sometimes you can't necessarily assume that the way it's written down in the book is how it actually is, because when they set up this machine, they took a lot of shortcuts, because we don't have 10 sender frames, we only have 1 frame and 2 senders, so they just could have, for instance, cut off, half of this crazy chain circuit that's going on, because what's the point of having this giant chain circuit if we're never going to use it? So there were a bunch of question marks around that. Then back to the whole converging thing, we had to operate a series of relays in the sender. So we got through the point where the sender gets called in. It gets past 2 pieces of information right away. It gets past the district frame number that the call is originating from. We're sure that's working right. It gets past the class of the caller, so like what type of subscriber is the calling party. I'm sure that's right. And then it checks that. If it checks that and it succeeds, which it is, then it operates a vertical select magnet and a horizontal select magnet and a vertical hold magnet to lock in the frame indication, and that's happening. Once it's locked in the frame indication, it proceeds to go ahead and do one final check to make sure everything is like it should be, and then it goes through a process to release the link frame and inform the subscriber end of things that it is ready to accept dial pulses, and yes, you can close the tip and ring loop from the subscriber through me right now because I am good to go. And that's where this convergence is happening. So Andrew and I looked at it for a few days, and we finally observed that the L relay was operating too soon. And that's weird. Why is it operating too soon? So we traced that back, and we got ourselves into a big mess. So that L relay is the one I got from our storage, and I hooked it up, and I thought I did it right, but I realized that I was looking at the wrong revision of a drawing. So I was hooking it up like revision 41 when I should have been looking at revision 13, that kind of deal. So, okay, it's very likely that I screwed that up. So then we went back, and that's what I'm doing today, is I'm going back and undoing everything that I think I might have done wrong, and then manually checking all of the different leads that surround this relay. Anything that comes close to it in a logical sense, I'm going to tone out and make sure that it's going where I think it's going. The other thing that I did is that the resistors that are in series with the winding of that relay are 1%ers. They need to be extremely tight in tolerance, which I just looked at and found out, and I've been sort of fudging the resistors because, you know, it's close enough, it's within 10 or 20 ohms, it's fine. In this case, it's not fine. It needs to be right on the nose. So I went through our stash of resistors. We have, at least in the museum, we have several hundred, and I found one that is, you know, this important one that's exactly dead on 850 ohms, and I replaced that. So that was also an improvement. So what I want to do is actually talk a little bit about the L relay and what it does and why it's so important. And what I'm going to do is not use the relay that's in the sender. I'm going to use a similar relay that's a little bit larger that I can point to. And it's okay, it's not the exact one, but it operates in the same characteristics. So we'll talk about that real quick. Alright, here we are with our fake L relay. It's not the same one in the sender, but it operates the same way, and it looks the same. Primarily, this one is just bigger, so I can point things out to you, and this one's actually meant for telegraph use. But again, it's the same principle, so might as well just use this. So this looks very different from a normal relay that you'd see in a telephone office. This relay is actually polar. And what that means is, instead of operating when the current is on and not operating when the current is off, it operates either this way or this way, depending on the direction or the polarity of the current. So this, underneath it has a horseshoe magnet that runs around like that, and the magnetic flux, the magnetic circuit, can go either this way through the relay or this way through the relay, and this armature can either go left and touch the front contact, or go right or touch the back contact. And when the relay is not energized, the armature can either sit in the middle, which it usually does. Now, these are both the contacts here, so you can adjust them with these screws. And then back in here, you see some other screws in the rear. Those adjust the distance of sort of the magnetic poles from this movable armature. So if you move this one closer, the armature would be biased towards this side and rest here. And if you move this one farther and this one closer, the armature would be biased towards this side and rest here. Ideally, when these relays are adjusted, you usually want the armature to rest somewhere in the middle. And if you look carefully, you can see that it is doing that, because I can push it either way, so these are properly adjusted. Now, the complicated part about the L relay in the sender is as follows. Unlike this L relay, the one in the sender has 3 windings, a primary, a secondary, and a tertiary. And all of the windings have very particular number of turns and a very particular resistance. In the sender relay, the first one that gets energized in sequence is the tertiary winding. Now this is important. The tertiary winding tends to bias the relay towards the back contact, which is the one to this side. So as the sender is getting ready to close the tip and ring circuit through so it can accept dial pulses, the relay goes from being neutral, as in not energized, to biased towards the back contact, this side. What was happening in our case was that some wiring was wrong, and I haven't figured out what specific wires yet. I'm going to work on that when I'm done shooting this video. But there was wiring that was wrong, and instead of biasing towards the rear, it was biasing towards the front. So it was operating towards this contact prematurely, and then causing the whole rest of the circuit operation to happen prematurely, and everything else after that, just the big cascade of failures because we weren't expecting that to happen. So I was able to disconnect every wire except the secondary winding, and then go ahead and energize the operate path for that winding. And now, as of just about 10 minutes ago, it's operating this way, so it's biasing towards the back contact, which is great. That's exactly what I want it to do, and that's a really good sign, because as long as that part works, I can prove that that tiny part of the circuit is correct. I just have to go through all the other wires I hooked up and figure out why they're interfering with that bias. So the reason we have that bias towards the back contact is because when dial pulsing is happening and the relay operates in this direction, the electrical bias has the effect of when the dial pulse is over, when each pulse ends, the bias pulls the relay back quickly towards the back contact. So if your dial is kind of, if the pulses coming in from your dial are either are gross, basically, on the line because of resistance and capacitance and all that pixie stuff, it will make sure that it always pulls itself back and disengages fully, and that causes your registration in the rest of the circuit to be really positive and really good. Happy pixies. Now the secondary winding, which I haven't gotten into yet, is not biased in this direction. It's kind of biased a little bit in the forward direction. Now what that tends to do is, on the secondary winding only, there's a capacitor in series with that. It's called the pH capacitor, which means pulse hold. Now, as we know, DC current doesn't ordinarily pass through a capacitor. So this relay operating on DC, why is there a capacitor in here? That makes no sense. But what the capacitor does is it tends to, again, even out the dial pulses coming from the subscriber's instrument. So if the dial pulse is really short, too short for this relay to operate long enough to cause the cascade of other things that have to happen, the stored energy in the pH capacitor will be released and serve to keep the relay operated for just long enough to ensure positive operation of everything else in the chain. And if the dial operation is too long, let's say there's the opposite problem in the subscriber's dial, the pH capacitor will charge fully and then not allow any more DC to come through and hold this relay operated any longer than it should be. So this capacitor is basically just a device that's going to smooth out the operation of this circuit so that it doesn't operate too long and it doesn't operate too short. And finally, the primary winding is actually the real operate path for this relay. And the primary winding is directly in series with the customer's dial itself. So you have a circuit running from the central office, from battery, through the customer's phone, through their dial, then back in through this relay, and then to ground. And this relay is sitting right in the middle of that circuit. The primary winding, specifically, of this relay is sitting right in the middle of that circuit. So when the subscriber's dial releases and then makes and breaks those pulses, that's what operates this relay on the primary winding. The secondary winding and the tertiary winding are just helpers to make sure that this operates at exactly the right time and for the right length, because the operation and release of this relay affects a whole chain of subsequent events that have to happen at exactly the right time. Otherwise, the sender will record an incorrect digit. So if I dialed a 5, the sender might record a 3, and it's obviously totally bad for a whole number of reasons. So that's why this relay is really important. And the chain of events that is caused by this operating and releasing is critical towards the entire rest of the operation of the sender circuit. This is the L relay in schematic form, and we can see the 3 windings. This is the primary winding. This middle one here is the tertiary winding. And this one is the secondary winding. Starting with the tertiary winding, we can see that there's 48 volts through 850 ohms of resistance through the winding, and then up and out to ground. It gets ground from the make contacts of this other ON1 relay, so when the ON1 relay operates, this ground path is closed through the tertiary winding to 48 volts. And if you look closely, you can see that the tertiary winding is oppositely poled to all of the other windings, and that's what introduces that reverse bias that pushes the contact spring towards the back. Now the secondary contact, here's 48 volts. Sorry, let's start here. Here's 48 volts. Here's this condenser, the pH condenser, and then it goes out through a bunch of other stuff and eventually gets ground over here as well. So this condenser is basically the air that makes sure that the operation of the primary coil is held and released when it should be. And finally, the primary coil, here's 48 volts in the central office, through the primary, out of the sender. I'm going to zoom out a bit. Out of the sender, out of the central office, through the subscriber's dial, which is not shown on this diagram, then back into the central office, into the sender, and to ground. So this is the primary operating path for this relay. So what I'll do is I'll spend the next couple of hours toning out all the leads and making sure that everything's connected right. I'm sure I'm going to find a problem or two. And then I'll come back either in this video or probably actually in the next video, because I just want to get this one uploaded. I'll come back and we'll move through the rest of the test frame.